So Leonardo will chair the first session, and I give the mic to the.
Right. Thank you for the introduction, and with that, I would also like to take the opportunity to thank the organizers for putting together this very nice workshop and giving me the opportunity to discuss some of our recent work on making quantum materials using microwave photons and superconducting circuits. And today, I'll particularly focus on our recent work on making the strongly correlated photon fluids in interesting ways. Okay, so the motivation behind these experiments is to the fact that we understand the class of interesting and complex quantum phenomena in condensed matter physics that involve various classes of many-body models that have an ensemble of interacting particles. And we want to understand this phenomena in order to expand and improve our theoretical framework, and also to sort of improve our technological capabilities. And of course, these problems are hard to simulate because it's exponentially becomes intractable to simulate these problems on a classical computer. So there's been extensive and growing efforts in trying to engineer quantum systems that are tailored in order to simulate the quantum phenomena of interest. And in the past 30 years or so, there have been a large number of efforts in having individual control, manipulation, and characterization of various quantum systems. And in this talk, I'll discuss about interacting microwave photons in superconducting circuits. As a pedagogical overview of quantum simulation, you have a target Hamiltonian of interest, where you either want to figure out what is the ground state of the system, or you want to understand some complicated many-body dynamics. There are generally two approaches to do this. There's the digital approach using a universal quantum computer, where the idea is that you want to characterize your Hamiltonian by decomposing it into a set of local 1 and 2 qubit gate operations over finite time slices, and you repeat this sequence many times to improve your accuracy of implementing your model. The nice thing about this approach is that you only need a few number of elementary single and 2 qubit gates as part of your gate set, but you need a lot of resources. You need a lot of gates, you need a lot of qubits in order to improve the accuracy of simulating your model. But once error correction kicks in, this approach promises a universal quantum computer, a universal simulate. Then there's the analog approach, where you want to implement your model Hamiltonian directly in the lab. And the nice thing about this is that if you can implement your model, it can be simulated very efficiently. But of course, this type of approach is limited in the fact that the disadvantage of this is that you're only limited to simulating only a certain class of many-body models, provided that you can implement this in your lab. The nice thing about this approach is that you are less prone to errors as you are in the digital approach. So you can perform more efficient quantum simulation without having to worry too much about not having a universal quantum computer. And the research that I'm interested in doing implementing these models and making analog simulators with superconducting circuits. And in the circuit QED community has developed a lot of the tools that you would need to implement these artificial quantum materials with microwave photons. There's been a lot of efforts in confining photons in lattices of microwave resonators that gives them an effective mass similar to electrons in a solid. And then you can harness nonlinear circuits composed of Josephson junctions in order to mediate interactions between photons. And the fact that you have dissipation, and as we'll see later in this workshop, actually is not a bad thing. You can even leverage dissipation to engineer reservoirs where we can efficiently thermalize certain many body states. And we can also have interesting ways in which we can introduce artificial gauge fields and look at topological materials. And we can put all of these ingredients together, and there have been a lot of nice efforts in various groups where we've implemented Hubbard models with superconducting circuits. But as you put all of these ingredients together to reach your target Hamiltonian, that's just the beginning of their journey, really, because what you're equally interested in, and it actually is quite challenging, is how can you prepare entangled states in such a large quantum system, and how can you actually tell that you did it? It's a complicated non-local measurement. So there's this idea of guiding your many-body system to desired state. It will be the theme of this talk, and it actually branches into, it's not just important for many-body physics, but it's also important for quantum information and quantum enhanced metrology. So this will be the theme of this talk today. And obviously, it's worth emphasizing that this idea of performing analog quantum simulation was first pioneered, called atoms, for very good reasons. You have that the atomic systems are very clean systems. All the atoms have the same energy, and they have internal states that are long-lived. So let's see, in comparison to that, you have superconducting circuits. These are macroscopic quantum objects. They're going to have a lot of disorder, as I'll show you later. Because of that, so not all the circuits are going to have the same energy, so you need additional hardware overhead in order to correct and combat this disorder. And since we're dealing with photons, we also have to account for dissipative losses. So, I always like to start as a pessimist, and maybe this is not the ideal way to start a seminar, but, from a grand scheme of things, it doesn't seem like using microwave photons and superconducting circuits does not seem like a very nice platform to do quantum simulation. But as we've seen these past few years in our group, we've actually tried to turn this argument on its head by using some of these disadvantages as resources or as tools in order to make quantum materials with microphotons and these types of circuits. Okay, so here is the outline of my talk. I'll first cover sort of the basics of our quantum circuit platform and kind of introduce what are the main building blocks and how we can make actually materials from microwave photons with the capabilities that we have and could have later in the future. And then I'll focus on several experiments where we essentially, there are going to be just two topics. I'm going to cover new preparation schemes where we can assemble solids and fluids of microwave photons, and also interesting new ways to probe non-equilibrium processes where we can look at transport of excitations and also trying to make phonons of light. Okay, so the material we're trying to make is actually quite simple, for the experts in the obvious. This is a Bose-Hubbard model. The elementary particles in the system are going to be the microwave plasmon excitations in our circuits. We want to engineer sort of an artificial lattice where these photons can tunnel between different lattice sites, and we want to engineer some interactions or where there's going to be an energy cost due to have the two photons repel or attract each other. And it's this competition between the kinetic energy and the interaction potential that gives you strongly correlated phases. In this case, you have a mod insulator, a superfluid phase, showing in this phase diagram here. And sort of this competition that we're trying to leverage in the system. So how do you implement this model where, as physicists, we like to describe everything in terms of harmonic oscillator operators. So when you try to make this model, well, let's just try to see how we can make microwave oscillators. Let's just make everything out of microwave oscillators. And the simplest and our most favorite oscillator to make in the lab is just an LC circuit, right? You have an inductor shunted by a capacitor. You have a parabolic potential. Each quantized level corresponds to adding a photon in the system. Of course, you wouldn't be able to do any type of quantum computing or quantum simulation if you just had linear circuits. So in order to, as I said, we have to introduce interactions. What you do is, well, the easiest thing actually that you could do is you replace this inductor with a Josephson junction. And This essentially gives you this on-site Harbor-U interaction. So there are many ways to think about what happened here. Well, for the physicists in the audience, it's essentially now instead of having a particle quantized in a parabolic potential, now you have a particle quantized in a cosine potential from the Josephson energy. This gives you this anharmonic energy spectrum. You can also think of it as that every time I add an additional quanta, an additional microwave oscillator, it essentially changes the inductance, because you can think of this Josephson junction as a nonlinear inductor. It changes the inductance by about 40% every time you put in just a single quanta, and that's very nonlinear. And for the nonlinear optics people in the audience, you can also think of this as an oscillator with some Kerr nonlinearity. Okay, so but eventually what we want to make is some oscillator it's a weakly anharmonic oscillator where you have that you need to pay some energy penalty to put in an extra quanta into the system. We can easily measure this in the experiment. Here I'm showing you the spectroscopy of when you go to the ground state, vacuum to the first excited state, 1 photon, it has some resonance energy. And if I repeat this experiment again, but I have 1 photon into our qubit, we will see that it has a different resonance frequency, and this energy difference between them, that's basically the interaction penalty that you need to pay in order to put in an extra particle, an extra microwave photon into the system. Okay, so we're going to use this qubit, we call it the transmon qubit, as a lattice site where we can localize a photon, but of course we want this photon to be localized over many lattice sites, over many qubits. So how do we couple them? Well, quite easy. We just put in a capacitor between 2 qubits, and now we just recover the physics of 2 coupled oscillators, where if I have 2 qubits that are in resonance each other, and I start with 1 photon in 1 qubit, then I can this photon will slosh back and forth between these two qubits, as shown in this measurement done here, where I'm looking at the probability of 1 qubit is a function of time, and it oscillates at twice the tunneling energy. So that's how we calibrate our tunneling energy. So we can combine these 2 ingredients, the on-site interaction for the Josephson junction and the tunneling dynamics given by our capacitor, and we can reach the one-dimensional Bose-Hubbard model where, again, so we have a tight binding lattice where the lattice sites are these blue crosses. These are our transmon qubits. And we have our quantum particles. The photons are tunneling between different lattice sites and are experiencing strong on-site interaction because of the Josephson nonlinearity. So everything that I'm going to cover in this talk, once we make this device, the tunneling rate J and the on-site interaction U, these are fixed. Once we make the device, we put it in our dilution fridge. So the only thing that we can control in situ is the potential profile of our lattice. Basically, we have on-site control of the lattice disorder, and we're going to use this as much as we can. Okay, so this is a more zoom-out view of the machine. I already described the time binding chain of transmons. This is where the science happens. And one thing that I skimmed over is the fact that we don't just use one Josephson junction, but we use a superconducting quantum interference device. It's a superconducting loop interrupted by 2 Josephson junctions. I'm going to skip through the technical detail, but basically, if we have these lines where we pass in DC current, and these lines are inductively coupled to this loop, we by threading some magnetic flux, this allows us to tune the energy of the Josephson junction, allows us to tune its effective inductance, and that's one way in which we can tune the resonance frequency of all of these transmons. So this is how we can have in situ tuning of the lattice profile and potential profile and disorder. Now we can do on-site spectroscopy, on-site microscopy of each lattice site by dispersively coupling each qubit to some readout resonators. And the way we do this is basically we have that the response of this resonator depends strongly on the state of the qubits. As I'm showing here, transmission for these readout cavities, they have different transmission depending on if the qubit is in the ground state or in the excited state. I'm showing you the same data, but in quadrature space, in phase and out of phase IQ components. So you can see that obviously we can't do APDs. We can't just measure single microwave photons because of temperature. So using the dispersive trick, we can get very good single shot fidelity to map the population of each qubit. To map if we have one photon or no photons or even two photons in each lattice site at any point in time. Okay, so, and then let me conclude by saying what are kind of the parameters of our circuit. So the lifetime of just a photon living in one of these qubits is, they can live somewhere between 10 to 100 microseconds. So this is the equivalent lifetime, decay rate. So in comparison to this, we have that our tunneling energy, our tunneling rates are about 3 to 4 orders of magnitude faster than this. So we're in this quantum coherent regime where we can tunnel the photons between lattice sites much faster than they get into the vacuum. And then we have that our interaction strengths are now an additional order of magnitude stronger than our tunneling energy. So actually what we're dealing with is hardcore bosons confined in one dimension, right? You have on-site interactions about 10 times, 20 times larger than the tunneling energy. Okay, so I finished sort of what were the building blocks for our circuit platform. So let me cover some experiments where we've go through several schemes of using some of the imperfections I mentioned before to prepare solids and photon fluids. I'm going to describe certain preparation protocols and how we're actually, in the fluid specifically, going to probe the ordering of photons by looking at two-body correlations and also entanglement between lattice sites. But first, let me, given that the topic of this week is about using dissipation for many body systems, let me tell you how, in the previous work, we used dissipation in order to stabilize a Mott insulator for photons. And in order to do this, we needed to make we had to engineer this funny looking reservoir, as I'm showing here. So to make this reservoir, basically, I want to make an object that refills itself with exactly one photon every time it's empty. And the way we do this is we're going to use another transmon. It's just another anharmonic oscillator. And I'm going to excite this oscillator to the two-photon state with some two-photon transition. And then I'm going to introduce some energy-dependent damping, some energy-dependent dissipation. How? Well, simply I'm going to couple this oscillator with another LC circuit that has a lot of damping. And I'm going to have this LC circuit be resonant with a 2-to-1 photon transition. So why is this dissipation energy selective? Well, this allows me to have the two-photon state decay very fast to the one-photon state. But because this is anharmonic, this dissipation is not going to affect the lifetime of this photon, the single photon state. It won't decay to the zero-photon state except its intrinsic lifetime. So by applying this two-photon drive and having this dissipation coupled to the system, then that's how I can refill this reservoir with one photon. Okay, so now let's just take this reservoir and couple it to the edge of our time-binding Hubbard chain. And what's going to happen? Okay, well, this photon, obviously this reservoir is resonant with these lattice sites, so this photon will it will tunnel to this lattice site, and then of course this reservoir will refill itself with a photon. Now in this specific time, nothing's going to happen. I can't have this photon tunnel into this lattice site because again you have this large interaction penalty to have double occupancy in this lattice site. But eventually this photon will tunnel to its neighbor, which will allow this reservoir photon to go into the lattice, and then you kind of repeat this procedure until you reach a unit filling of one photon in each lattice site, and this is what we call a Mott insulator, a photonic Mott insulator in our system. This is a cartoon. Here I'm showing you the data for the temporal dynamics of the lattice site occupation, and you can see there's some wavefront. There is a wavefront of the lattice occupancy here, and you reach some unit filling Mott insulator. And the reason why you stop filling photons into this Mott insulator because you have this many-body gap. You have this large energy penalty that prevents any other photon to kind of go into your Mott insulator. And it turns out that this dissipative stabilization technique works really well for any type of incompressible phase. As long as you have a many-body gap, this thing can work, because essentially you have this reservoir where you can irreversibly pump particles into your system while also removing entropy from it. Now, of course, this is one-state preparation if you have this many-body gap. But what happens if I don't have such a large many-body? Yes, question. Yes. Yeah, for cartoon purposes, I put here as U is positive, but yeah, our U is attractive, U is negative, so I can kind of show diagrams of calculated band, of calculated energy levels, and basically you're just gonna your many-body spectrum. So normally, say ground state, because in this case, our ground state is like the highest energy state in some conserved number of particles manifold. Yeah, but I just drew it in a way that's more, more clear for people, because we're normally used to positive U repulsive models. Okay, so I want to segue into the fact that if you want to prepare compressible states like fluids that don't have this, yeah. Oh yeah, so that's a very good question. This was done with 7 lattice sites. I think the challenge is if you make a long, you will have, and if you just have a stabilizer at the edge, it will take some time for it to fill, and essentially you're just going to compete with the lifetime of the single site lifetime of your photons. So you can go as large as you want. You just fabricate your circuit, but eventually you just want to also have like larger coherence in order to see this wavefront filling front. Also, you can think of ways in which you can maybe if your chain is too long, you can have a stabilizer at both edges and maybe also somewhere in the middle. So obviously, there's more hardware. The longer the chain, maybe you need to put in more stabilization hardware to reach a decent fidelity of preparation. Okay. Yes. Mm-hmm. Mm-hmm. Okay. If I have an attractive U, and I keep increasing the number of particles, yeah, then you will have, it will climb and it will just go down, and yeah. One thing I should say is that when I describe these states as having a Hubbard U term, actually that only works well for the first 3 or 4 levels. You should really think of it as a particle in the cosine potential. So if I need to have more than 2 or 3 photons in each lattice site, then writing it down as the positive U term is actually not correct, because you're ionizing yourself to the point where your states just go negative, and that's not allowed. So this description is fine if I have at most double occupancy in each site. And for the many-body manifolds that we're interested in, right, then you're not going to have this problem that you mentioned. But the many-body gap is still there. It's just that it might not be exactly the anharmonicity U if I have more, if I have, like, say, a Mott insulator with a filling fraction, a unit filling of 4 on each site, then I have to treat it more as like as a cosine potential. Yeah. Mm. Yeah, I think that's a much better. Yeah, thank you. That was a much better answer. Um, is that the? Can't you? So you kind of. The point is you can't have a BC if it's attractive for you. Mhm. I generally like to think of it's a photon blockade in the sense that you still have to pay an energy difference to to go from a manifold where I have no more than single occupancy per site to one in which I have double occupancy, which is sort of like these manifolds that drawn here, except that they would be flipped. So essentially, you apply your drives and you eventually stabilize yourself to kind of like this one state, and then you just have this energy gap that prevents you from having double occupancy. This would be this reservoir. Mm-hmm. Yeah, it is a non-equilibrium process. You're just trying to stabilize yourself through that manifold. Yeah, you'll remain this manifold here. Yeah. Okay, no, but these are really good questions. So again, yeah, it is a nonlinear process, right? You keep pumping in photons into this reservoir that keeps dumping the photons into here. So yeah, and I'll keep coming back to pictures of the many bispectrum, but with negative view. Hopefully it's less confusing. So to quickly kind of go to the next topic, where of course, even if this is a small size system, increase the system size, you'll always have this gap with you. But what happens if you have states where this gap is small, and you have compressible states? How do you prepare those? And I'm going to describe a different preparation scheme where now instead of using dissipation, we are going to use another imperfection in our system, and that's disorder. And let me guide you through this forest of many diagrams where we're going to use disorder. So the first order of business is we're going to introduce a lot of disorder into the system. Here are the lattice they're detuned in energy by more than the tunneling energy J. So this allows us, if we put a photon into the system, or basically any type of multi-particle state, just basically corresponds to a product state where each photon is just localized because of disorder in each lattice. And how do we put the photons? Well, that's easy. We just have some calibrated microwave pulses where we resonantly drive these sites to put in our particles. And then we adiabatically, or we slowly remove disorder from the system. So this process needs to be adiabatic in order to remain in the same instantaneous eigenstate. And as we slowly bring the lattice into resonance, we have, through tunneling-induced quantum fluctuations, that these particles will be localized into some correlated fluid. And at the end of this, this procedure where we ramp the disorder to near zero, we're going to use on-site microscopy to look at on-site densities, measures of correlations, and also entanglement. So let's warm up by simply just trying to see how we can just localize one particle into our Hubbard chain. And basically, this just corresponds to melting single particle momentum states. Here I'm showing the diagram of energy as a function of disorder. Here it's showing time, but I'm varying disorder as a function of time. So it's strong disorder. Here I have that each state corresponds to just having one photon localized in one specific lattice site. And then as I vary disorder adiabatically, I'm going to eventually prepare some momentum state here with some momentum, quasi-momentum Q. And again, adiabaticity just ensures there's a one-to-one connection between where I put my photon in space and which quasi-momentum state it delocalizes into. So here I'm going to show you the data where I'm going to show the on-site densities, right? Because we have dispersive readout. We can show what is the population on each lattice site as a function of disorder. This is what the density looks like as I start here. And here I'm going to show you in real time what the density profile looks like as I go to various disorder realizations. So you can see that this particle eventually delocalizes into some sine of kx quasi-momentum state. And I can also do this for the next quasi-momentum state where actually it's quite nice because you can see that we initially start in the photon in the middle and eventually just delocalizes into a wave function that has a node in the middle. Okay, so we can prepare these single particle momentum states. We have to be adiabatic. I didn't quite specify how we probe adiabaticity or how we ensure that we are adiabatic, because obviously to be adiabatic, you can probably ramp the system for a week just to be safe, but your photons won't live in a qubit for a week. So what we do is we use reversible state preparation as a way to benchmark adiabaticity. What we do is, okay, we just melt our particle the same way as we did before, but now we're going to ramp the system back to the initial disorder to relocalize the information into each qubit. And the idea is that if you want to be adiabatic, then you need to be able to come back to the same initial state. That's how we simply, one way you could do it is, okay, let me just do tomography on the system when it's some entangled state across all the qubits. That's not maybe so easy to do, but it's much easier to kind of relocalize the information and just look at single site occupations. So this is the experiment I'm showing right here. We are varying this ramp time that's done symmetrically over about 4 orders of magnitude. It's an exponential profile. I can go into details later over coffee. And we're looking at this metric for benchmarking adiabaticity as kind of the overlap. This overlap wave function basically tells you what's the probability of reaching the same initial state. And you can see that, okay, so when our ramp is very fast, it's much faster than the tunneling rate, then obviously I'm still going to recover the initial population, but no delocalization happens. Qubits come into resonance and they come out of resonance much faster than it takes for that one photon to even go to its neighbor. Okay, and then once we go a little bit slower, then we are going to go through some Landau-Zener transitions, leakage into other qubit states, which results in a decrease in the population in our initially populated qubit. This is when our ramp rate is about 1 over j or less. But then once our ramp rate is a bit slower, we recover our initial photon, and we use this ramp rate to calibrate our adiabatic protocol. And you can see the point I was trying to make earlier is that you have this competition between the need to be adiabatic and also the fact that you have a finite lifetime for the photon to live in this. So obviously, we have a small finite size system, and it just works out that we can be adiabatic for some amount of time, here a couple of hundred nanoseconds, before we have to worry about the loss of a photon from a lattice. Okay, so we use this protocol also now to do the real thing, which is to melt multi-particle fluids. Here I'm showing you a complicated landscape of the many-body spectrum, where we can split the spectrum into manifolds of here's shown as a function of disorder. We're going to split it in terms of manifolds of fixed total number of quanta of photons, and then each manifold then gets split again into a fixed number of overlapping particles. And what we're going to focus on is these hardcore bands, where we're going to have at most 1 photon per lattice site. And here I'm zooming in to the free particle manifold, where we want to stabilize, we want to prepare this free particle fluid, where we start the large disorder by occupying the free highest qubit states and disorder, and then we ramp the disorder to near 0 to delocalize our photons into this correlated fluid. And let me show you the data of the density profiles as shown in real time as we ramp the disorder. from strong disorder around 10J to something that's close to zero disorder. So again, the particles are localized, but then as you get close to zero disorder, you get these particles delocalized, shown in this density profile. And we can do this measurement not just for free particles, but here I'm showing you sort of this delocalization for 2 particles, 3 particles, and 4 particles. Again, this is in lattice sites. That's why I'm showing you the normalized density. So you go from a localized regime to a delocalized regime. And one interesting point that you see, yeah. Yeah, I absolutely agree. We actually, essentially the way we looked at it, or at least I looked at it, is with, okay, let me just, the worst case, the next worst case scenario, okay, I'm gonna have some leakage to this state. Disorder, exponential was close, but essentially, yeah, you can do first order optimal control, like have your ramp sheet to kind of match that gap as a function of disorder. There's some extra complications where like, okay, our ramp sheets are a bit distorted. You want to send an exponential, but that's not going to be exponential as it goes into your sample just because you have frequency distortion for your microwave cabling. So that's where optimal control can come in, right? It turns out that we're still exploring it, but the one thing that we're hitting a roadblock is that we need a lot more data than we anticipated just because there's so many free parameters. But this is definitely something we're thinking about, also ways in which we can maybe try shortcuts of adiabaticity, where like we can actually go a bit faster than 1 over the gap. Just because, if you make the system bigger, it becomes harder to do the traditional adiabatic approach. So there are definitely more ways in which we can improve this. Okay, so here I'm showing you the density profiles of our delocalized fluids for 2, 3, and 4 particles. And one nice thing, you see that the shape of these density profiles actually are different, and they depend on the number of particles or on the density of particles you have in your system. And this already tells you there's some insight into how interactions play a role here, because these photons are delocalized, so they experience these interactions. And in fact, these interactions are actually shaping these density profiles. One way to think about it, you can do some easy numerical calculation where, okay, let's see, if I just had no interactions, then all the density profiles should just match that of the single particle case. Of course, you have to rescale it by a full number of particles, but it should all just be some, just some cosine wave function right here with some confining factor. Now, if you have interactions, then in your many-body wave function, then you have to add this interaction, these contact interaction penalty that when 2 particles are on top of each other. And if you do this calculation with this many-body ansatz, then actually you get a density profile here. So 3 particles, it kind of matches nicely the experiment. These dashed lines actually correspond to, I'm not sure if you can see the theory. So this indeed shows you that the ordering that comes from the delocalization and interactions, matches kind of sort of this intuition that we have in one dimension. But a nicer way to probe ordering is to actually look at some correlations and some entanglement metrics. Yeah. Yes, it does. So we just do that, the plot I showed where we do that calibration routine, we do it for multiple particles as well. And, it's about a factor of 2 or 3. So like, actually, it turns out if you are, the way we stagger, because we like to do in a zigzag filling, if you have half a filling, actually, that's where the gap is easier to work with. So actually, that's where you can be the fastest. You just think about your neighboring states, and the gap is you not just first near zero, near degeneracy, but as you transverse through disorder, actually near half a filling is the nicest to work at, which is actually the most complicated state you can prepare when you have half a filling. Just because if you have particle Hall symmetry, of course, which is what we have. We have particle Hall symmetry. Okay, so to look at ordering, we're going to look at particle correlations. One correlator we can look at is this conditional particle detection metric. We're going to look at the probability of detecting a photon at site I in space, like, qubit site I, conditioned on having a photon detected at site J. It corresponds to this correlator. Here I'm showing you the data for having two particles in our lattice where we have to simultaneously measure two lattice sites in the same time. And here I'm showing you this correlator as a function of sites I and J. And here I'm showing you some cuts. And one thing you can see that there's a clear, when I equals to J, then this conditional metric is exactly 0. This is just from the fact that our many-body wave function is 0 when two particles are on top of each other. This is just a hardcore constraint. And another thing we see is that the wave function has some curvature near I equals J. And this is telling you that the photons are also trying to lower their kinetic energy as they get close to this I equals J barrier. So the picture that I like to think is that, so if you have these are strong measurements, and you have these interactions. So what happens is that you start in a two-particle in a box fluid, and then when I perform this strong measurement, that basically pins that one photon to be, it kind of projects that many-body wave function, which pins this photon to be in this lattice site. Now the second photon can't be there, so this actually acts as a potential barrier, and you go from this two-particle in the box to a single particle deconfined in two boxes. So you can see that this projected measurement interactions are actually shaping the wave function of this two-particle fluid. Oh, 5 minutes. Okay, I'll try to go a bit faster. Then you can look at pair correlation functions. This is G2, where you're just looking at the basically the probability of measuring two particles at some distance x from each other. Here I'm showing you the G2 as a function of different lattice fillings. It matches nicely this model for a parameter free model for Tangge-Girardot gas, where you can basically see that you have a region of the spatial anti-bunching that scales with the density. That's intuitive because as you put in more particles into this fixed volume, you basically, the photons have less space to delocalize into. So this anti-correlation region scales inversely with the density. And then when we rescale this x-axis with the density, all the points kind of collapse onto this universal Tangge-Girardot theory where we can see some tiny oscillating correlations. These are Friedel oscillations that are basically a signature of the fact that our strongly interacting photons confining them in 1D act as free fermions. And then you can also look at entanglement metric, where we're looking at the loss of purity by measuring the density matrix of each lattice site and basically probing how much one qubit is entangled with the other qubits by looking at the loss of purity and averaging over all the qubits. Here I'm showing you the data for free particles. You can see that near large disorder, you have no entanglement, and as you ramp the disorder to 0, you increase this entanglement metric. Now, of course, purity decreases also if you have dissipation, and one way we can tell that this increased entanglement doesn't come from a loss with some dissipative environment is we essentially ramp the system back to the same disorder configuration, and we recover basically the same sort of entanglement metric. So this tells you that this increase in entanglement that we see near zero degeneracy genuinely comes from the fact that the particles are delocalizing and essentially mediating entanglement between the two. So sorry, I'm going a little bit fast, but so this covered the part where I looked at preparation schemes and kind of looking at the ground state properties of these fluids. Let me quickly kind of go through ways in which we can look at non-equilibrium properties where essentially the idea is we're going to look at spectroscopy of collective excitation, superposition of many body states, and specifically in these fluids, we're going to prepare some phonons. The idea is that we're going to both leverage our adiabatic control of our disorder, but also we're going to add in some intentional perturbation. So we're going to melt particles into some perturbed state, and then we can quench the system in order to prepare some superposition of both the ground state, but as well as some excited configurations to look at dynamics. We can probe excitations in the system by looking at the AC susceptibility. One way to do this is we prepare these fluids, and then we AC modulate the one lattice site's potential and look at the density response on the other site. This is basically, this response function corresponds to, through the Kubo formula, to the AC susceptibility. So I'm going too fast. This is the data where, we modulate these fluids and we look at the lattice density response as a function of the modulation frequency. It's a bit complicated to look at, but if you want to look at the spectral response, take the Fourier transform of this data set, you can see that most of your data is along the linear response regime. So if I shake this fluid at omega, it's going to respond at omega. If I'm going to drive it faster, it's only going to respond at 2 omega, 3 omega, and so on. But if we look at the linear response regime and extract the signal along the linear response curve, here I'm showing you data where we can, you see quasi-particle peaks for 1, 2, and 3 photon fluids. This is AC susceptibility, it has some spectral decomposition. So what these peaks correspond to are basically the energy detuning from your ground state to some excited state configuration. We can do more than just do spectroscopy if we shake the system for some amount of time and for a variable frequency. And then again, relocalize the information as we tune the disorder back to strong. If we look at the original localized sites, we get some chevron patterns, we get some oscillations, and these are actually oscillations between many body eigenstates, where I go from the ground state to some excited state and actually prepare nicely some superposition of many body eigenstates. This is showing you how our spectroscopy, it's finite size, so I only can get dots, but it agrees nicely with what you expect in theory from a structure factor calculation. And one nice thing is that you see that the low-lying dispersion in energy versus K is linear, so we expect to have phonons in the system. So the way you prefer phonons is basically the way you slosh a cup of water, is that you melt your particles on some cosine potential, because you want to essentially excite the low energy, long wavelength excitations, and then we quench it to degeneracy to prepare these superpositions, and we can see sort of dynamics where we have some wave packet that's traveling back and forth between the two edges of the system. And you can actually see that the sound velocity scales with the number of particles or the density in the system, and that's what you expect for free fermion theory in a Tonks-Girardot model. And we can see that this is our measured sound velocity is a function of lattice filling or lattice particle density. I'm almost done. And you can see it nicely matches the particle hole symmetry that you expect in a free fermion model. In this last minute, let me just skip to I kind of like this, so I just want to see what your response is, but in this 1 minute, maybe so great. But I've shown you ways in which we can go from a frame where we have a quantum computer where the qubits are delocalized. I can apply gates between them, and then I adiabatically melt it into some material that's an entangled fluid. But if I adiabatically come back, it's still going to be at this boring product state. So there have been ways in which we thought about how we can perturb this fluid in order to come back to an entangled state. In this case, it's a Newton state in our quantum computers. And the way we do that is essentially we stagger our system such that we prepare unit filling of 1/2 on one side and the other side is empty. We melt the system to degeneracy, but now one of these qubits is detuned by the interaction strength U. And if we don't have double occupancy, right, if this state is not available, if I adiabatically come back to a reverse staggered composition, these free photons are still going to be on the left. But now if this ancilla middle qubit is excited, then I can delocalize these particles into a fluid. And if I adiabatically come back to this reverse stagger, now these free particles have switched to the side. And this is my final state. So one interesting thing is, okay, what if my ancilla qubit is in a coherent superposition of 0 plus 1? Well, this is what's going to give me at 0 disorder, a superposition between being a solid and a fluid. And as I come back, that's going to be my Newton state. So, this is the data. Here I'm showing you what the lattice profile, density profile looks like when I have a solid plus a fluid. The joke is this is quantum custard because custard is non-Newtonian. And as I come back to the final state, obviously the density profile should be uniformly 0 because this is a highly entangled state. So one way we can probe entanglement is using many-body Ramsey interferometry, where this ancilla qubit that processes at some natural frequency when it's not entangled with the other qubits, you see that it processes at a much faster frequency that you can probe by applying your gate, waiting some time, undoing the gate, and you can see this precession frequency is faster and given by the energy difference between the two manifolds that you're entangling. And what I'm saying is that you can change your system to have energy offsets, and you can see that your Newton state sensitivity scales with the system size. You can see that your many-body spectroscopic peak shifts as a function of the system size for both 5-qubit Newton state and 6-qubit Newton state. So, okay, so I'm just going to summarize with that. Of course, please let me acknowledge the team. This was done in the Schuster and Simon labs. This work was done in Chicago, but right now we're in the process of moving to Stanford. Let me acknowledge the grad students, Brendan, Gabrielle, and Meg, who are part of the quantum simulation team, our tier support from Kagan Hazard. This was the outline. We're looking at just Hubbard models with on-site interactions, new assembly techniques, new types of probes. I think as an outlook, I would like to look at extended Hubbard models where we're looking at not just on-site interactions, but interactions over longer ranges. If you just change ways in which you couple your qubits, you can have just nearest neighbor interactions. You can look at some extended Hubbard models where you can get density weights and as well as some symmetry protected topological order. And this is something I'm actually trying to do in my new research group that I'm starting in this spring at the NYU, and I'm looking for motivated students and postdocs to join me and do quantum research in the heart of Manhattan. Thanks so much for your time, and you can answer any questions you have. Thank you.
Occupation on every other site. Curious.
Yes.
I mean, what happens if you suddenly switch off this order and you study the out of equilibrium dynamics? Because so far you showed this adiabatic evolution, but you didn't show any real out of equilibrium.
Yeah.
dynamics.
So that's the quench part that I discussed.
Yeah.
But that part also includes some adiabaticity.
Mm-hmm.
So that is a very good point. And let's see. So if you just quench, you just like localize photons, put them in, and just bring everything into resonance, you're basically going to navigate the entire fixed number particle spectrum, right? And that's basically looking at the quantum random walks. People have looked at that physics for single particle as well as multi-particle physics. Here we wanted to approach it a bit differently in the sense that, okay, let me first, choose what kind of states I want to have superposition of, right? Because if I did what you suggested, it would kind of be, I think, a superposition of all of these states. And in this case, it's more localized in energy in the sense that if I just want to look at the low-lying energy spectrum dynamics, that's what you would do. One interesting thing that we can do is also we could, instead of doing a cosine, we can do sine kx for different. That's actually how we can actually momentum resolve some of these excitations by kind of melting to some potential profile to just match some mode profile and then quench them and look at dynamics, and that will give us the peak that we want to find.
Right, but the reason why I'm asking is that, there are precise predictions also for that situation, and actually there are some, very interesting things to see there. So this is why I was wondering.
Yeah, I'm happy to talk about them.
Okay.
I imagine the theory, once you have particle Hor symmetry and everything's in one dimension, but once you break some integrability, then maybe it becomes harder to migrate. Yeah, but I'll be interested to talk about. Yeah.
Okay, thank you.
Okay. Yeah, I was wondering what's your T2? So I guess it's worse than T1, and are you?
Oh yeah, T1s are around 20 to 80 microseconds. T2 Ramsey, so without an echo, are a few microseconds. But they get a bit better once things are in resonance because you create sweet spots. And T2 echoes once we just have a single dipole cycle around 10, 20 microseconds.
So during your evolution, T2 plays a role, and you don't really care because it's just multi-insulator physics, or?
For the fluids would matter, especially if you want to probe coherence. We just happen to go just like right at the edge, like fast enough compared to T2. But I think once we go to degeneracy, because T2 just comes from the fact that if you look at the energy as a function of the tuning knob, that you tune disorder, but that's magnetic flux, and flux has some classical noise spectrum. That gives us a T2, but once we get close to degeneracy and things are coupled, then you have that dispersion kind of creates some sweet spot, right, because of these avoided crossings. But yeah, when we look at many-body Ramsey for other probes of coherence for the gate, as well as for we're also doing compressibility and chemical potential, we do see that the contrast in our ancilla just decreases because of T2. So everything that we see in terms of performance is coherence limited. We do play echo schemes to increase the coherence. Yeah.
Johannes?
So that's a good point. I know I skimmed over it, so I'm happy to discuss it later. So for the phonons, yeah, we're looking at superposition of states in the same conserved number of particles manifold. But as we melt, then we can have one of those qubits being a superposition of 0 plus 1. That's actually how we can melt states, superpositions that are in different number manifolds. And I skimmed over it, but like it's really nice. That's actually a nice way for us to probe chemical potential and compressibility, so we can do both of those things. And the way we check it is we just look at the total density and see how it compares with n times omega or n. And if we do this dynamics for very long times, much longer than what we do, then we do see a significant loss of particles.
So still on this negative U. So in the plot that you show for G2, this is still for the very large U, but negative, right? So that should be more like what people call a super Tongzhire, the state. Should be like the filling function 1, but strongly attractive interaction. So you should see a difference that, I mean, this state should have a stronger oscillation at KF compared to standard Tongzhire. I don't know if you've ever seen a difference.
No, we have not. I mean, like okay, maybe this is where my understanding is different, because like if U is positive or negative, but like super large, I can just think of this as spins, right? An XY model and mapping that to a free fermion model is just Jordan-Wigner stuff. So in that sense, there is obviously a J over U correction to things. So maybe that's where the thing plays a role.
Yeah, indeed. That should,
but
yeah, of course, you need.
For us, that's 1 over, it's 1 over 25. So it would be small to C.
Okay.
Like, we don't even see that difference very clearly in the sound velocity.
Okay.
To be fair.
Okay.
Is it quick?
No, but it's not really a question, it is just a comment, but just now I understand the stuff about the U negative. I was spoiled because I'm used to think about the continuous case, but it's really because you are in a lattice that you have this maximum energy state.
Yeah. Okay.
And then it's fine.
Yeah.
Okay,
Thank
so
you.
I propose we put
Yep.
here, and we thank Andre for the beautiful talk.
Já falamos assim que essa marcha.
Lena for this session of the morning, and particularly to thank her because I know yesterday she had a horrible trip to Paris. So thank you very much. Please.
But I think Leonardo was staying up very late last night to try to help everyone to arrive safely from the UK. So I will talk today about novel non-equilibrium phenomena in quantum speeds of light. I would like to start by just acknowledging my group. The picture is a little outdated. We have many new members, including Harvey, who is here, and some already left, but we just never came across to change the photo. And especially I would like to thank Paolo and Cristobal, whose work I'll be presenting here. So starting to motivate, although after the first talk of this morning, probably we don't need a kind of strong motivation for what I'll be talking about. But in general, in our group, and we have been working on photons which do interact. Yeah? So forming various states, fluids, solids, in the case of interacting photons. So this all started a while ago already, thanks to huge experimental progress in the last decade or two. It was possible to create photons which would interact the photon will interact with other photons via some matter components. For example, in case of semiconductor microcavity via excitons, or in the case of superconducting circuits, as we just heard, via Josephson junctions and nonlinearity of the circuits. In case of cold atoms in cavities, they'll be interacting via cold atoms, and in case of other platforms, via some other nonlinearity. But obviously, photons are never equilibrated. There is always some Brayton dissipation, so this gave rise to the whole area of looking at non-equilibrium, phase transition, critical phenomena, superfluidity, topological defects, and transition in this driven. So that was the kind of what people were concerned in the last 10, 15 years. But recently, and also as we heard in the previous talk, it's also possible, in addition to interactions, it's also possible to add external potential photons, placing them in one-dimensional or two-dimensional lattice structures, leading to yet a new area of quantum solids of light, which you can create in materials, while the underlying building block is a photon, it's an interacting photon. So I would say that maybe I'm biased, but probably currently there are two dominant systems where these interacting photons in lattices have been explored. One system, which we already heard earlier, are superconducting circuits, where especially it's very easy to engineer very strong interactions, and there is an exceptional high degree of control of the system. Whereas, as far as I am aware, they still struggle a little with disorder, and it's very easy to scale up that platform. So alternative platform, which I will mainly talk about in this talk, is semiconductor microcavities, where instead of, the nonlinearity here was provided by circuit PD, nonlinearity via Josephson functions. Here we have excitons, so the structure is MBA grown. We have quantum web electron hole pairs interacting strongly with photons, forming new particles called polaritons, and then polaritons between themselves can interact via this excitonic component. So obviously here quantum effects can be done up to room temperature. Even room temperature condensers have been reported in some organic materials. Those are quite easy to prepare and read out, and obviously can be easily integrated with other platforms if you think of technologies. But unlike these systems, we are not yet in a very strongly interactive regime. So the difficulty here, obviously polaritons interact much stronger than cold atoms, but they do not yet interact as strong to give a clear signature for the case and going to, let's say, if you think in terms of superfluid to multi-insulator transition, to go into the 1 particle per size. Probably at the moment around 100 particles per lattice size. So this is the biggest chunk. And that's in the community at the moment on the experimental side. This is what is occupying the experimentalists mainly to go into this really strong photon blockade regime where you can create a 1 polariton per lattice size via optimizing confinement, via creating open cavities where one can place surface acoustic waves and put a very strong periodic potential for photons, or alternatively going into different schemes such as OPO in lattices where perhaps the interactions are not very strong, but you can create a correlated photons via OPO regime, and if this is scale up to lattices, you can create some strongly correlated states without very strong interactions via different means of correlations, the excitonic Feshbach resonance explored, and also dipolar polaritons. So excitons and photons, where the electron and hole pairs is placed in a different quantum well, leading to a dipolar exciton, which has a much stronger interactions. And if this can be coherently superimposed with the normal, because such a state does not couple to light very easily, but you can create a coherent superposition between direct and indirect exciton, leading to dipolar polariton, and that would be both interacting with photons as well as having stronger interactions. So this is another direction. And when we get there, obviously there's a lot of proposals looking at all kinds of strongly correlated phenomena, which we already had in the previous talk, even going to states which lead to fermionization of photons, fractional quantum Hall state, Majorana model. That proposal has been theoretically predicted once we achieve the strong photon blockade. Okay, so this is just kind of a very brief introduction to what is the state of these interacting photons in the semiconductor context. But before we go to this strongly interacting regime, obviously there is a lot to explore, kind of interacting systems which are not as strong interacting as to go yet to the multi-insulator. So we basically have a condensate, but a condensate with a drive and dissipation. So something not the same as cold atoms or liquid helium or some other condensate because of this driven dissipative nature. And obviously polaritons are probably leading the field of non-equilibrium superfluid in a kind of weakly interacting regime, but there are also photon BEC and obviously circuit PD systems, atom cavities, and others. So basically we can ask a question, okay, we definitely can engineer something which is very close to equilibrium in that system, the superfluidity, Bose-Einstein condensation, all of that phenomena have been observed, but can we engineer states which are out of equilibrium, but they are interesting, they are non-trivial, there is something novel in that in context, in contrast to cold atoms. So obviously, since I'm talking about it, obviously there is hope and such states have been seen and quite a lot of them. And in this talk, due to the time limitation, I pick up just 3 different topics which I would like to highlight for the kind of novel non-equilibrium phenomena you realize in these driven dissipative condensates of light or photonic condensates, polaritonic condensates. So I will talk about phase order phase transition. So where in case of cold atoms or in liquid helium, we just have a condensate. We might have a thermal cloud of the condensate, but we don't have really any other particles. And probably the same applies to circuit PD, that we just have photons. In case of semiconductors, obviously, as you can imagine, we have a lot of mass of the semiconductor itself. You have excitons, you have excitonic reservoir, you have phonons, you have all kinds of details of the semiconductor physics. So this is the situation where a coherent, where a condensate is coupled to classical fluid. And you might think, okay, that's not good, we don't want that, but in fact, it actually leads to quite a nice phenomenology, which has a lot of analogy to classical systems, to statistical system, and to biological systems such as active matter. Such analogies have been already recognized. I myself participated in 2 conferences which organizers were trying to put together quantum community of quantum fluids of light as well as biological community. So people looking at active matter in a biophysics context. So I will talk about that a little. Then I will move, we have the whole session, I believe, next week on KPZ. But we have done quite a lot of work on KPZ, which is another non-equilibrium phenomena very specific to driven dissipative system, to active matter. And so I will talk how our light matter condensates can be a good example of those. And then if I have time, I will talk about condensation in Landau levels. So now moving from two-dimensional quantum fluid to solids, and how we can engineer condensates in the lowest Landau level, which means we have a natural rotation in the system, and system will be spontaneously breaking time reversal symmetry in that context. The screen. Okay, so before I talk about those non-equilibrium features of polaritons, I want to say that for many years, the holy grail of the field was actually to see equilibrium. We wanted to see equilibrium BC, we want to see equilibrium BKT. And if you think of photonic systems, obviously, the photonic system you don't have a three-dimensional option for the photonic system. Your system can be either zero-dimensional, one-dimensional, or at most two-dimensional, because you need to trap photons in at least one direction. Yes? Yeah, I mean, that's because it doesn't really show, but maybe this one is stronger. Oh, green one, yes, that's the good one, because the screen is not, oh yes, it's much better, the green one. So polariton condensates can at most be two-dimensional, and we know that in 2 dimensions, when you have interactions, the relevant phase transition is actually costless-Thouless, not a BEC. So vortices at the boundary of the phase transition vortices, well, depending which way you go, either they bind into a vortex-antivortex pairs and annihilate, or they proliferate and unbind and you create a disordered phase. So the polariton community was looking for an evidence of such an equilibrium BEC, and that was possible to achieve only in the second or the third generation of samples, which had particularly long photon lifetime in the cavity. And indeed, it was possible to see a very clear, so costless-Thouless transition is characterized by vortex proliferation at the phase boundary, but also algebraic decay of first-order spatial and temporal coherence. So such algebraic decay clear algebraic decay of spatial and temporal coherence has been reported already about 6 years ago. And moreover, it was the first system where both space and time spatial coherence was possible. So in any other system, such as cold atoms, helium, you can only measure spatial coherence, not possible to measure temporal coherence. With photons, obviously, it's easy to measure temporal coherence. And indeed, it was shown that both exponents, as dictated by the theory, were the same as in equilibrium and smaller than a quarter. So, and if you look at theoretically at the problem, you could see binding and unbinding vortices as you cross the phase transition. There were some caveats to that if the samples are not as good, if your lifetime is shorter, you could have non-equilibrium BKT, which exceeded this theoretical upper bound set by equilibrium physics. So you created some overshaken condensates, where overshaken superfluid, where you put much more collective excitations before vortices proliferate, but it was nevertheless quite similar to equilibrium case. So since then, we're interested, okay, we tick the box of achieving equilibrium of the Thouless transition, but we wanted to see what else we can do with that system. And that led to the two topics which I will mention in the introduction. So first thing is that, okay, let's say my microcavity is not so perfect. I need to drive the system quite strongly to sustain a steady state. And I create a lot of excitons in the system in addition to my polariton condensate. So I have a coherent fluid, which is now coupled with a reservoir of incoherent fluid. So something, again, probably not so easy to realize in liquid helium or cold atoms, but here you can go to different level of reservoir versus condensate population. And what you could see is that this reservoir creates an effective attractive interaction between polaritons. So normally polaritons have repulsive interactions. Adding a bit of reservoir creates a repulsive interaction. And that leads to, sorry, the attractive interaction, and that leads to fragmentation, to self-trapping. So as you increase the size, one does not go from disorder phase to an order phase automatically, but you go in via pattern formation, via a condensate which is non-uniform. Yes, so you have in these puddles, in these islands here, there is a condensate, and there is a disorder state in between. As you increase the drive, you finally reach a perfect condensate. And when you examine the transition between this and that, you see that there will be a first order phase transition. So if you measure the number of vortices as you go across the transition, correlation length, and all the observable, you have an abrupt jump. And also close to that, obviously our system is finite, and we know that every first order phase transition in a finite system corresponds to bistability. So in this region close to the transition, for exactly the same parameter, you could either be in the uniform condensate or in this pattern-forming condensate, depending on your, I don't know, noise or a specific case in the simulation. So you have a bistability here as well. So looking, and even doing the evolution, you could, our driving here is completely uniform, and yet the system phase separates. So you have a region here which has a beautiful, nice condensate, and a region which is fragmented at the same time. And there is nothing really which would set this length scale. We don't, everything is periodic boundary conditions. The system is drive uniform, and yet you have this phase separation. So this is another thing which is characteristic for the phase order phase transition. And then when you look at what's happening between, so when we go from disorder to our superfluid via this first order phase transition, but when you look at the puddles, so you can see that you have vortices. Maybe it's not so easy to see on that picture with this contrast, but you have vortices binding and unbinding in the system. So you have basically BKT and first order phase transition happening in the system as you go across the phase transition. So there are a lot of systems which do that. Yeah, so like why is it interesting? Okay, we have some BKT coinciding with first order and some pattern formation. Why is it interesting? Well, so these equations, when you look at them mathematically, as well as when you look at the result of simulations, actually are quite analogous to models of flocking of self-propelled particles. So if you want to look at fish or birds, how they order themselves from completely a disorder configuration to order configuration to go via this pattern formation. There is a lot of similarities between that. And also coexistence of first order and BKT has been reported in XY model and active matter, where you have XY model a little bit more complicated than the usual XY model, so where the interactions between spins is also kind of angle dependent. You can also see that. So it seems that this presence of this incoherent reservoir is introducing us the physics which are quite similar to, let's say, XY model with theta-dependent interactions or the active matter type of interaction. So that's already a departure from the usual BKT, what we are used to in cold atoms or in helium. In cold atoms, I guess, the transition is not taking place, not taking in the same way via kind of inhomogeneous formation of a condensate before we reach a homogeneous condensate. So that's quite different. But something which is yet even more different and interesting is Kadar-Parisi-Zhang physics, which I will show that is also happening in the driven dissipative context. So we will have the whole conference about that. We will hear about a lot, I believe, from other speakers. But since I'm the first one to talk about it here, I just mentioned just briefly why we are interested. So KPZ is a universality class. It's relevant for a wide range of non-equilibrium phenomena, especially in one dimension. So ranging from surface growth, paper, bacterium colony growth. So a lot of biological and classical soft condensed matter problems are described by the KPZ equation. And to date, at least, although some people might argue, but today there is no clear experimental realization of KPZ in 2 dimensions. So all the experimental cases are in 1 dimension. And moreover, and this I can say with certainty, there is no any other system when my variable will be a compact variable. So all the other examples of KPZ are for continuous variable. In our case, the variable which will obey KPZ equation in the case of driven dissipative condensate will be a phase. And phase is a compact variable. It only goes from 0 to pi, and one can have vortices there which competes with the KPZ order. So this is the first experimental realization, well, possible experimental realization of KPZ in 2D for a compact variable. So obviously I have no time to derive why our system obeys KPZ equation. You have to believe me, but that's where it comes from. So a driven dissipative condensate will have amplitude and phase. And you can now treat the amplitude fluctuation to second order because they are gap as in any other equilibrium or non-equilibrium condensate. So you can integrate them out from the problem. And if you integrate them out, you only obtain an equation for the phase. So if you do that for a system without drive and dissipation, so for cold atoms, liquid helium, superconductors, you will have only the terms which are not highlighted in pink. So that will just be the usual equations for the phase in XY model, which gives an algebraic decay of coherence in the case of ordered phase or exponential decay of coherence in the case of disordered phase. Now, when you have dissipation, and especially it's important to have nonlinear dissipation. So linear dissipation will not contribute to this term, but nonlinear dissipation would. So if you have some terms in your Hamiltonian which are complex, I something which is nonlinear, or if you have some reservoirs coupled to your system which in a nonlinear way, and you integrate out the amplitude fluctuation, you obtain additional terms for the phase, which are now nonlinear, which are quadratic. So this is dx theta squared. Yeah, theta, by the way, is the phase of the condensate. So what does it mean? Well, what it means is that now, in principle, you have a different behavior of the phase, and at large distances, this will not lead to algebraic decay, but it will lead to stretch exponential decay with the characteristic KPZ exponent of 0.37. However, if you for a moment forgot that theta is a compact variable, you just don't take this into account, despite the fact that you have stretch exponential decay of correlation, superfluidity should survive. So that was some work already quite old by Ruth Altman, Lucas Kieberer, Sebastian Gier, who I believe will be here at some point. Phi is the phase of the condensate. Oh, sorry, phi, what is phi? Yes, sorry. Yes, sorry. So, okay, this is what I've taken. Say. Well, I mean, it doesn't matter. It doesn't really matter because okay, so, okay, it could be the theta, but it could be the field. Yes, so because the amplitude fluctuations are gone. Yes, so the only fluctuations are in the phase. So, okay, so this is the whole field, because that's what you can measure in polaritons. Let's say the whole field. But if you decouple that into amplitude and phase, the phase will have similar behavior because amplitude fluctuations are non-existent or not negligible in this case. Yes. So at this is a field. Yeah. The way this is written is E. So yeah. Okay. So so that was discovered a while ago, and it was proposed that this system would be really interesting to study KPZ. However, later on, it was discovered that when you consider the compactness of the phase, there are problems. So I will summarize what was discovered, and I will describe why that is the case. So it appeared that KPZ order is actually not possible in the steady-state thermodynamic limit in the case of compact variable, because it will be killed by vortices. It will be killed by vortices in two ways. So if you are, if you look at systems away of the phase transition, that will be killed by the usual BKT type of vortices. When you look at the system very far away from the, so close to the phase transition, they will be killed by BKT vortices. Away from the phase transition, there will still be a single vortices which will destroy the coordinate setting the thermodynamic limit. So if you want to limit a system to the small size, smaller than the distance between these vortices, then it appears that we still see power decay of correlation for the system size. So the length scale for vortices is actually smaller than the length scale for KPZ. So that's a kind of answer, but I will explain why that's the case. This is the case because if you now compute the force between two vortex anti-vortex in the KPZ equation, which was done by analytically by Sieberer in 2018, then you see that that part, which is attractive, normally vortex and vortex pairs have attractive interaction in the XY model. That's why you have a BKT transition, because they attract each other and they annihilate at the transition. However, here in the KPZ, they acquire additional term, a negative term here. And this term can be either positive or negative. So you could enhance this attraction, or when it becomes positive, so you have minus here, it might lead to a situation where vortex and anti-vortex pairs repel each other. And there is a crossover at some length scale. So for small distances, always attract each other, but for larger distances, they may repel each other depending on anisotropy. And it turns out that for anisotropic system, this term dominates at long distances. So if the vortices are formed, they will never come together and annihilate as in the BKT scenario, but they will repel each other. And so now, that was a prediction which was based on a lot of approximation, and especially experimentalists were skeptical. I mean, if you perform 100 different approximation mappings into the charges, into electromagnetic dual theory, which no one understands apart from Fabi here, then, you know, for experimentalists, this is not clear. So we did exact simulations of the KPZ equation with the compact feature. And indeed, if you take isotropic system, whatever you do, you just end up with extremely disordered phase. There are millions of vortices here. You can zoom in here and you can see there is a disordered phase. Now, it was quite interesting because it was done by our master student. You just change a sign in your equation. So just to remind, I probably should, if you don't remember what these equations were, this is the equation, and it's important, the anisotropy. So lambda x, lambda y. If lambda x is equal minus lambda y, we have something called strongly anisotropic case. If lambda x is equal lambda y, we have isotropic case. And obviously, there can be any ratio between the two. But one opposite to the other, so lambda x equals minus lambda y, is strong, what we call strongly anisotropic, and it's quite an interesting case. So if the system, you just change a sign in your simulation, all of a sudden, you see that the vortices are completely gone. You have strongly anisotropic, you have no vortices and beautiful coherence. Sometimes if you run another time, you might see a few vortex-anti-vortex pairs. So just by changing anisotropy. However, again, it can be shown with renormalization, that in the strong anisotropic case, the vortices are gone, but the nonlinear terms are irrelevant in the RG sense. So you obtain just the usual XY model type of physics, so no vortices, but also not KPZ scaling, but you just obtain the usual algebraic scaling. Quite pessimistic, because either you completely kill your KPZ phase in a way that you have complete disorder, or you kill KPZ phase in a way that you have complete order. Yeah, so either by order or by disorder, we are killing it. So, okay, this is a singularization. Obviously, singularization means nothing. This is done by using truncated Wigner simulation. It means nothing for a single singularization. We have to run it thousands times. And indeed, if you look at phase ordering, in case of isotropic case, you see that this will, for different strands of this anisotropy, of this nonlinearity, KPZ nonlinearity, you will see that it will saturate eventually to a large number of vortices. On average, if you have stronger anisotropic case, you do phase ordering from a disordered state, it will actually order completely, all the vortices will decay to zero. Yeah, so you have what is kind of expected. And what is nice, so the solid line is our simulation, sorry, the dotted line is our simulation, and the solid line is taking this potential, which was predicted by Lucas Sieberer, and writing down hydrodynamic equations of motion analytically for the dynamic of the condensate and predicting analytically what the dynamic will be, and they coincide exactly. So despite these approximations, actually, they got this potential quite well. Okay, so it might mean quite pessimistically, because here the universal behavior as in FY models is something that we know and maybe are not so excited about anymore, and here is destroyed by vortices at this length scale. So, okay, but that's only very kind of limiting cases, isotropic or strongly anisotropic. So perhaps there is another way. We can maybe help with anisotropy, but in a weakly anisotropic way. So this is something which we have proposed, and I will just discuss in a moment. And also there are some other ways, which I presume you will hear in the session about KPZ, that if the system is not completely continuous, but if you make it on a lattice, so in case of the Jacqueline Bloch experiment with the micropillar, I guess Michiel is here, so if you have any questions, you can ask him. But if you put it on a lattice, you also kill some of the observe the KPZ scaling. So if G is very small, I need a massive system to observe KPZ because it's in an exponent. If G is larger than 1, I should see KPZ at all length scale, and indeed we could see a window where that should be possible. Again, sorry. Yeah. So again, that was done in a very similar way to earlier analytical work, so Keldysh field theory, the normalization group, and so on and so forth. Experimentalists might not believe you. If you do this, it's always better to just brute force simulations to convince anyone. So motivated by analytical prediction that this KPZ phase should indeed exist in this OPO system, By the way, I should mention that analytically, we map that OPO system to the KPZ equation, whereas here we have 3 amplitudes and 3 phases. So the algebra is a little more advanced, but only 1 phase is gapless. The other 2 phases and all 3 amplitudes are gap. So you can, it's a little more troublesome, but you can still integrate them out, and you obtain equation for only 1 phase, which is gapless, yes, which is of KPZ form, with some caveats that I have no time to go on the caveats. So now, okay, you can do that, or you can just take your OPO microscopic equations and simulate numerically. It's quite a heavy numerics, but you can do it. And what we see is that, so this is a phase diagram. For the OPO, you always have upper and lower thresholds. So as you drive, you switch on OPO, you have a very nice condensate, and then finally you kill your condensate if you drive too strongly. Yes, so you go up and down. And as you can see, the blue and green are quite a strong condensate, but they are still weaker than red. Yes, so naively I would expect that if I take red, the decay of coherence in red should be the slowest, because this is the strongest condensate. And yet what we see is actually that the decay of coherence in this case is the fastest, and when we feed it to the stretch exponential decay, it gives us very good feed with the universal exponent. So universal exponent is 0.39, 37, our best fit is 0.39. So this suggests that indeed in that window, so we have this window here, which should be, so the red is within KPZ window, the blue and the green is outside of the KPZ window by analytical prediction. And indeed, numerically, this gives us much faster decay of coherence and very good fit to KPZ. Then, motivated by actually referees, something which is a smoking gun for observation of KPZ phase is to look at the phase fluctuation between T0 and T0 plus delta T. So if the system is obeying KPZ equation, it has been found that it's not symmetric, that it has this kind of special form. So the red is the one from the paper, and our analysis blue show that it agrees very well with that, whereas if you just take a simple Gaussian, you can not agree. So it means that really we see KPZ in that. And then another question could be, perhaps it's a transient. So it has been discussed of 5 minutes. Yeah. So we can ask a question. Perhaps it's a transient. So that we are starting from something which is mean field. We are at noise. The systems have no time yet to develop these free vortices and kill the KPZ phase. So we started from something opposite. We started with a noise initial condition, which means that we have a lot of vortices. And as we simulate in time, these vortices decay. This simulation took half a year for my student to do. He was doing other things, but it's really very long because you have a very you have critical slowing down, especially which you are not far away from the transition. But eventually, we could see that number of vortices, anti-vortices, eventually decay below 1 pair. So it really went to a vortexless state. So we believe that it's a really a free vortices-free KPZ in this case. However, it's interesting to note that the phase sorting was slower than in the case of XY model by factor of 2. And that's also interesting because probably what's happening is that still in KPZ, our interactions are modified. They don't have the same form as in XY model. They have this negative term, so they are weaker, and that probably what leads to a slowing down in the phase ordering. Okay, so just the conclusion of this little introduction is that in theory, if you just think in terms of true equilibrium, true steady state in an infinite system, in isotropic case, KPZ scaling is not possible for compact fields. They will always be filled by free vortices. However, it could be possible only in finite system or as a tangent. But still, if you just take an isotropic system, we always have a situation when the vortex length scale is smaller than the KPZ length scale. However, this can be tricked. And one way to trick it is to introduce weak anisotropy, for example, in the OPO. And another way to trick it, which we'll hear later in this conference, is by putting the system on a lattice and looking at the KPZ on a lattice, which apparently also helps in realizing KPZ. So since I don't have, I have only 5 minutes, I probably skip that topic. It's creating polariton strain graphene, which has been done by Alberto and Jacqueline, and looking at some states which are, I mean, without putting any external rotation, the condensation is happening into rotating states in the Landau levels, but I have no time to talk about that topic. So I probably should just finish off mentioning that in our group, we are also working quite a lot on developing methods for driven dissipative and correlated systems. So as you know, this light matter system, the circuit PD, which you heard in the previous talk, polaritons, photon BC, they are all driven dissipative, and the driven dissipation is strong. It's comparable to the internal interactions between particles. But at the same time, if these interactions are strong, if they are not just as weak as in the case of ultra-cold atoms BEC, then we have competing situation where the dissipation and interactions are of the same order. So then we need to think of what kind of method to be able to describe it. So we, in our group, we worked on the extension of phase space methods, which are generally very good for driven dissipative system, but maybe not so good for interacting systems. So we have some works extending those phase space methods to stronger interactions. And another way we also know very well, the tensor network are perfect for strongly correlated systems, especially 1D, maybe a little less good for 2D, but still good. But when you have 2D and driven dissipation, that becomes a challenge, and we also address that in that work. So I won't have much. How much time I have? A few minutes. Yeah, 1 minute. So maybe I just mentioned this because tensor networks is probably I won't even touch upon, but basically what happens is that the stochastic methods, especially truncated Wigner and positive P, are old. Yes, they were suggested by cold atom community ages ago, but they were not very practical. They couldn't calculate anything useful because the correlations are usually too strong, and the system will just the trajectories go to infinity. However, for open systems, this system now they kind of have the second life, because it appears that for open system, when you have a driven dissipation, these trajectories which used to escape to infinity for closed system now are stabilized, and they become a really very good tool to study driven dissipative system. And in that context, we propose positive P method to study, let's say, driven dissipative Bose-Hubbard model. So why this is so nice is because you can start from a strongly interacting system on a lattice, and you can map that to Fokker-Planck equations, and then Fokker-Planck equation can be mapped to stochastic equations without any approximation. So positive P is not actually bigger. You don't make any approximation whatsoever, but you map now strongly interacting system to stochastic equations. Stochastic equations are relatively easy to solve. It's just that you have to solve it 1,000 times. So you are reducing your complex problem to a simpler problem, which you have to solve many times. And then you can control your accuracy by, obviously, it will be exact in the limit of infinite number of realizations, but you can always control your accuracy by making them a bit realistically smaller. And we studied that for the driven dissipative Bose-Hubbard, which actually might be interesting in the context of previous talk. And in that paper, we mapped where this positive P is very accurate. So if you are outside of this corner here, so this is a drive in the units of U, this is dissipation in the units of U. So if your dissipation or drive, either of them, are a bit larger than U is obviously the Bose-Hubbard U, then the positive P the positive P is an exact method. It always works. If you have an answer, it's always correct answer, but often it blows up and your trajectory goes to infinity and you cannot treat your problem. So if you can treat your problem, it's an exact, but sometimes you cannot treat this problem. So you can use positive P in that region of the Bose-Hubbard, and in that region you cannot. But at the same time, truncated Wigner is very accurate there because this is semi-classical regime. So this is 10 to the 12 to 10 to the 4 drive. Yes, we have a lot of particles, a semi-classical regime, so truncated Wigner is accurate. So only here, where your interactions are so strong that they are much stronger than drive and dissipation, only here you cannot use the stochastic method. But then you can, obviously, this is a good place to use tensor networks, and this is what we did, which I will skip, but if someone is interested in the details, it's published in that paper. It was done by my student Connor and now taken over by another student Jack. So to conclude, this second part, this method part, which I didn't have much time, I would say that dissipation, like in photonic platform, actually helps in performance of both stochastic and tensor network methods. I didn't have time to discuss the tensor network method because some of your entanglement is killed off. Yeah, you don't have entanglement of very large length scalars or very long time scalars because your dissipation is dumping it up. So, so actually these methods are actually become more useful. However, quantum correlation entanglement is possible to describe with this method. So it's not that you are only able to go to semi-classical regime and that is why it works. No, we have cases which is very quantum and still it's possible to describe with this method. But in our papers, we go to regimes which basically there is nothing to compare with. There is no other method to compare with. Some of our results, especially on driven dissipative spin models, which we didn't have time to talk about, and we actually need physical quantum simulator to verify that. And in terms of this light matter condensate, I guess I presented at least two and then touched upon a third non-trivial phase which can be engineered. So you can say, yes, that you can engineer non-trivial physics with driven dissipative condensates. Thank you, and I'm sorry for taking more time.
Other questions? Please. Okay, so.
Thank you. Thank you, Marjana, for a very nice and stimulating talk. About the first part of your talk where you say that there is this phase transition from unstable regime to a stable regime, it's when you increase power, no? With this,
from the inhomogeneous condensate to homogeneous.
Yeah.
Yeah.
Mm-hmm. So what about the experimental signatures for, because I know we have studied this also together with Jacqueline, and there we've never seen unstable condensates turn stable at large power.
This condensate is stable. It's just fragmented. But
it doesn't have good phase coherence in that regime, does it?
Yeah, of course not, because the puddles are in.
So exactly, that's the.
Yeah, but that's. I didn't have. I'm sure you will talk about it, or Jacqueline, that when you have, let's say if you want to do KPZ. Actually, it's ingenious that Jacqueline came up with an idea of putting it on a lattice, because if you take a polariton condensate and you want to create a large condensate, then you have this initially you have this fragmentation. Yeah, so that's why Jacqueline put it on a lattice and created a negative mass.
Exactly. Yeah.
Because otherwise, if you do that in that way, you won't create a uniform condensate. You will create these puddles.
Exactly.
And you cannot even study KPZ in that because your density fluctuations are.
Yeah. Yes, but you would say that by increasing power, it becomes
of course, by increasing power, but then you are very, very strong. Then again, you are very much outside, like after the phase transition itself. Yeah,
no, it's just that I'm not aware of experiments that have seen this, that you get good coherence. Eventually, yeah. That was the question.
Yes,
just
okay.
Whether...
that when you drive very strongly, that's a good point.
Okay, yeah. Mm-hmm. Okay, I have many other questions.
I don't know. I didn't think about it.
Yeah, maybe we can discuss.
Mm-hmm.
More questions? Yeah.
So I mean, so I've seen that. I mean, you showed many times the fact that the number of vortices decay, and for instance, you use this as a smoking gun evidence for the fact that you have a superfluid of the XY, like in XY model. But I mean, did you try to look also at, let's say, a more robust probe like alpha? If you measure the exponent of the 2-point of the decay, that should be universal with the. I mean, it should be continuously varying as a function of parameters of the model. So did you look at that? Or?
Yes, sure. So in this talk, I didn't show our work on XY model PKT transition. I didn't yet because there is no time. But, so obviously we have papers where we just study not KPZ, but let's say we are not in the regime of KPZ, we are in the regime of XY model. Yes, and we can see the vortices decay, you can see algebraic decay, and then we take alpha exponent, and then we can see how it varies in, and as I mentioned only in words, that in equilibrium you have this upper bound of 0.25. Yeah, we know that in equilibrium there is an upper bound. Out of equilibrium, there is no upper, I don't know whether there is no upper bound, but there is definitely, you can go above. And we went numerically up to 1.2. So what does it mean? So you could have exponent which is much faster, so the decay is much faster, but still algebraic. And this means that you put more sound waves, more collective excitations, then it's possible in equilibrium. So if in equilibrium, if I increase temperature, I put my sound mode, but finally I inject vortices, and I cannot put more sound modes than up to 0.25. Whereas here, I can put more sound mode before I proliferate vortices. So we call it like overshaken condensation.
Yeah, but at equilibrium, alpha depends on temperature, and out of equilibrium...
but it has an upper bound of 0.25, yeah?
Yeah, but if you fix temperature below the critical temperature, it changes and...
No, it depends on temperature, but there is a jump. So there is this universal jump in epithelium or alpha cannot go above 0.25. So
no, it cannot go, but it can go below. It can stay below,
yes,
and it depends on temperature.
But what I'm saying is that in this, if you are out of equilibrium and you compute alpha, it can go above 0.25. Yeah. We observe up to 1.2.
Okay, but my question was...
we don't even know whether there is an upper bound or not because it's all numeric.
No, but my question was whether there is a dependence on the parameters
yes,
you
of
can
course,
map
there,
out.
There is. Yes, there is.
Okay.
Yes, there is. And we have TRX 2016, which shows exactly alpha is a function of pump powers. But I was just not showing it here because I wasn't.
No,
I was talking about other things.
Okay, thank you. I tried to do this.
And what are the limitations of the tensor network approaches? Like how small, let's say, dissipation, how big system sizes you can reach?
So system sizes, this is in thermodynamic limits. So system size is not relevant of that one. Although Jack is now, like my other student, is now working on also changing the method to treat finite size systems because it's also interesting to study finite size effects in various systems. But this method, the particular one, is thermodynamic limits, and dissipation is basically obviously if you have huge dissipation, then you are really mean field. There's not strong correlation. The less dissipation you put, the more correlations you have, and eventually the method becomes harder. So you need to go to higher bond dimensions to describe. Well, we tested it for some exact method. You know, you can find Hamiltonians which have some exact solution and then test even dissipative, and you can test. So obviously, it's best to be in between because if you are very strong dissipated, there is no point with a mean field. It's nothing interesting there. If you have zero dissipation, then your system is too strongly correlated. You'll need a very large bond dimensions. So it's always best to be in between. So still there are non-trivial correlations, but the dissipation is helping you to stabilize the method. Yeah.
But in practice, like absolute numbers?
Oh, I would have to...
okay, we can discuss.
Yeah, because in relation to interactions, yeah, because you look at particular Hamiltonian. So we didn't. So this method was studied as spin model, so not on this bosonic interaction. It was mainly describing for XYZ models, XY models for the spin. And then one has to compare that interaction with dissipation. Yeah, because I don't have it on the slide here, but I mean, it always will work. It's just that you require higher bond dimension and higher to convert to the exact solution, obviously. Yeah. So.
Last question and then.
Thank you.
I was wondering, because you say so about this methods section, because you say you want to go also to strong dissipation, right? But you always start from some Lindblad description, and if you follow like a description of this quantum optical master equation, then you do a rotating wave approximation. So a Lindblad description would only be valid for weak coupling, right? So I was wondering if you also take non-secular terms or could you also go to non-secular terms by studying some Redfield description or so, right?
So now you are talking about strong
dissipation,
or like that you have some entanglement developing between the system and the environment.
Yes.
The dissipation. Yes, so with the tensor network, we started from Lindblad master equation. So there is no any way, it was just, weak or strong. We don't want to go to very strong dissipation because you will kill your entanglement inside. Yeah? Like we want to be in between, because if there is no dissipation. Okay, so in fact there is a little bit, although not on tensor network, but this diagram with U and gamma. Yeah, so if you have Bose-Hubbard model, and you have U, and you have gamma. Gamma is the dissipation, U is the interaction. So let's say this phase space method are working very well if U over gamma is smaller than 1. Yes, this was this other corner. And the tensor networks another way. Yes, so here for positive P2 work, this is really numerics. We've done lots of numerics to check that. You have to be gamma over U larger than 1. And tensor networks, so our algorithm which we employ on this bosonic system, on that one, you have to be on the other way. Yes, this maybe answers your question a little, although this is only
but
for
also
this
for this positive
model,
P, you started with some Lindblad, right?
So this, for this, yes, we have just Lindblad. This is a relatively weak dissipation. Okay. But this is not necessarily, okay, you can write down master equation and transform into Fokker-Planck, but you can also do it differently. So to derive this positive P truncated Wigner, you can also write Keldysh, and this is actually my preferred way of doing that. You can write field theory, and you can and then with field theory you have quantum and classical fluctuations, and then you can assume that I keep quantum fluctuation to second order, and then quantum fluctuation, if they're to the second order, they can be mapped to stochastic equation via this formalism, MSR formalism. But so you only assume that the quantum fluctuation kept the second order, but you can actually there, let's say if you wanted to have some color noise, so if you have some kind of memory in the system, this will translate to a color noise there. So you can treat, let's say if you wanted to treat some memory effects in your environment, you could do that via some colored noise, for example. I don't know if that answered your question.
Yeah, very well.
Because it's only non-Markovian effect you can treat. So in this, yes, I think in that would be very hard. Yeah, I don't know, maybe some people can do that, but we haven't done that. This was only master equation. So, but this is also in the limit of relatively weak gamma, yeah, so relatively strong U. So that's okay. Yeah, but so we treated this Bose-Hubbard model, we treated many different spin models, and it was always in this limit of relatively small dissipation, but still the dissipation helped the algorithm, but it was from the master equation without any memory. Here you can put memory via colored noise. You can derive it easily. We haven't done any numerics with colored noise. I don't know whether Michiel, you did any work with colored noise in truncated Wigner, but it's possible to put it, yeah. That.
Okay, so thank you very much, Michiel. So lunch is served upstairs. The meeting room up. 5 hours, wow. Thank you very much. I mean, I know it was a disaster for you, but the talk was really good.